Today we are diving into an exciting topic: fast and slow pointers, also known as Floyd's cycle detection algorithm. This clever technique is used to solve a variety of problems, especially those involving linked lists and cycles. By the end of this video, you will understand how this algorithm works, its applications, and why it is so efficient. Let's define the problem we are trying to solve. The cycle detection problem involves determining whether a linked list contains a cycle, finding the starting point of that cycle, and determining the length of the cycle. The main challenge is to accomplish all of this using only constant extra space, denoted as O of 1 space complexity. At its core, the fast and slow pointer technique involves using two pointers that move through a data structure at different speeds. The slow pointer moves one step at a time, while the fast pointer moves 2 steps at a time. Think of it like a race between a tortoise and a hare on a circular track. If a cycle exists, the fast pointer will eventually catch up to and meet the slow pointer, similar to how a faster runner will lap a slower runner on a circular track. Floyd's algorithm is executed in 2 phases. In phase 1, the primary goal is to detect whether a cycle exists in the linked list. Both the slow and fast pointers start at the head of the list. The slow pointer advances 1 node at a time, while the fast pointer advances 2 nodes at a time. The process continues until the fast pointer encounters the end of the list, indicating the absence of a cycle, or until the fast and slow pointers meet, confirming the presence of a cycle. Once a cycle has been detected, phase 2 focuses on finding the starting point of the cycle. To do this, reset the slow pointer to the head of the linked list, while keeping the fast pointer at the meeting point found in phase 1. Next, advance both the slow and fast pointers 1 node at a time. The point at which they meet again is the starting point of the cycle. This might seem like magic, but there is a mathematical explanation behind it. After finding the start of the cycle, the next step is to determine the length of the cycle. To do this, keep one of the pointers at the cycle start. Move the other pointer 1 step at a time, and count the number of steps it takes to return to the starting node. The count represents the length of the cycle. Let's delve into the math behind why Floyd's algorithm works. Suppose x is the distance from the head of the list to the start of the cycle, y is the distance from the cycle's start to the meeting point of the slow and fast pointers, and z is the remaining distance to complete the cycle back to the start. The total cycle length c is thus y plus z. Because the fast pointer moves twice as quickly as the slow pointer, we can derive that x equals n times m minus y, where n is the number of complete cycles the fast pointer has traversed. This equation proves that the distance from the head to the cycle start is equal to a certain number of cycle lengths minus the distance from the cycle start to the meeting point. Which explains why resetting the slow pointer to the head and moving both pointers at the same speed results in their meeting at the beginning of the cycle. Here is the complete implementation of Floyd's cycle detection algorithm in Python. This code defines a linked list node and a cycle detector class with methods to detect if a cycle exists, find the cycle's starting point, and determine the cycle's length. It's a concise and efficient way to solve these problems. The fast and slow pointer technique has numerous applications beyond just cycle detection. It can be used to find the middle of a linked list, check if a linked list is a palindrome, find the nth node from the end of a linked list, and even in cycle sorting algorithms. Its versatility makes it a valuable tool in algorithm design. In summary, Floyd's cycle detection algorithm is an efficient and versatile technique for solving a variety of problems related to cycles in data structures. It achieves a time complexity of O of n with constant space complexity O of 1, making it highly efficient. Compared to other approaches, like using hash tables, Floyd's algorithm offers the advantage of constant space usage and the ability to find cycle properties. While the implementation might be slightly more complex, the benefits often outweigh the costs. Thank you for watching. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.